Hello, my name is Haronian and I will speak about paper number 20, Production Process Evaluation for Earthworks. Production system in Earthworks is characterized by continuous processes of material processing, usually implemented by heavy machinery with the support of a surveying team and a material lab, and the products are continuous as well. They are linked to a geometry, to the existing geometry and 3D alignments, and at their lowest level of hierarchy in the location breakdown structure, we will find a linkage to the chainage of an alignment. And these characteristics distinguish between the production system that is required for earthworks and for linear projects as contrary to what we find in buildings. In this research, we will use machine control technology in order to monitor the production in earthworks. We will show how technology that is designed in order to enable automation of operations can be utilized in order to monitor and in order to evaluate production flow. The methodology of the research in general is design science research. The artifacts that we developed are production information schema and the production evaluation processes, and we validated the artifacts by a case study. That part of it is shown in this paper. The rodal information schema is the first artifact. It was detailed in a paper in ITCon 2019. Basically, it takes the continuous elements and divides them up into discrete elements, and each element contains the data regarding the design, meaning layers, elevations, types of materials, and it enables us to store data regarding the production process, meaning records of all the operations that have been performed on each discrete element, on each rodal. These road elements, enable us to aggregate discrete elements to work packages, and by that they can support work packaging of as planned and compare them to the as-made packages. The case study is a water reservoir, and we focused on the embankments that were produced by clay that was excavated on site. The operations we focused on were material supply, spreading, watering, and compaction, and of course the inspections of quality assurance, which were surveyor and a land laboratory. We recognized that the spread operation was the bottleneck of this process. It was recognized because of the high utilization rates of the resources in the spread operation, and of course the high amounts of work in progress that were found during the project, meaning that areas that were waiting for the spread operation to be performed. Another thing that indicated that the spread operation was the bottleneck was the queuing trucks waiting for supply of material, as we can see in the figure above. The data monitoring procedure was based on the rodal information schema. The embankment was divided into 75,000 discrete elements, rodals. The data was obtained by machine control systems and was linked to the elements, and accordingly we were able to evaluate the production, as I'll show. In the case study, we recognized two types of waste. One was overprocessing and the other was resource waiting time. Overprocessing we evaluated according to overfill. As we can see in the image, the design boundaries are in blue and the red area represents overfill, meaning this is layers that were performed beyond the design boundaries. The resource waiting time, we focused on the spread operation as it was the bottleneck. At the top view and the perspective view that we can see here, they show the track of a dozer performing a spread operation. In the perspective view, at the horizontal axis, it represents the time, and we can see these gaps. The gaps represent waiting time where the operation is not working. And these waiting times were evaluated, and of course the longer waiting times influence the production more significantly than short waiting times, and accordingly we designed a procedure to evaluate the resource waiting time. In the case study, we addressed 3 weeks of production. As shown in the figure, we can see the working areas and the elevations. The PPE index, the production process evaluation index, indicated significant opportunities for improvements as the results were approximately 50%. The calculation method is based on the value-adding products and the non-value-adding products, and the value-adding time and the non-value-adding time. This enables us to calculate the theoretical production that could have been achieved if all the time was value-adding and all products were value-adding. The ratio between the actual production and the theoretical production enables us to evaluate the production process and the PPE index. Further work that will be presented in a separate paper presents implementation of Little's Law and the principles presented in factory physics by Hope and Spearman, and 7 production metrics that we designed. I will show this in the following slides. In order to evaluate production according to Little's Law, we must define the throughput, the cycle time, and the work in progress. These are the basic parameters in Little's Law, and the calculation for these parameters is based on the Rodel information schema. And actually it's done for each Rodel, for each discrete element. Accordingly, we were able to present the evolvement of production through several shifts. In the upper part, we can see the WIP evolvement in blue. This is in intervals of half an hour per each shift. And we can see in the green the cycle times, and in the orange, yellow-orange, we can see the throughput. The cycle time, as it reduces, we can see some influence on the throughput, which correlates to the basic understandings of Little's Law. At the bottom part, we can see evaluation according to best case and practical worst case that were defined by Hope and Spearman in factory physics. The work of Hope and Spearman, of course, relate to discrete products. They relate to a penny factory. And in this case, of course, we're addressing a continuous production system of Earthworks and using the basic principles that they designed. We can see in the orange curves that they represent the best case, and in the throughput graph, the best case represents the highest constraint, the upper constraint regarding the throughput that can be achieved per each WIP. And we can see that in most cases, the results of each shift in the blue dots were below the practical worst case, that is in the gray curve. Some cases that was between. Regarding the cycle times, the shorter the cycle times, the better, meaning that's why the best case in orange represents the lower boundary, the lower constraint regarding the cycle times. And again, we can see that most of the results for each shift were above the practical worst case. Additionally, we assessed the production according to 7 production metrics. The first 2 evaluate the production reliability and compare between the actual production volume and the planned production volume, and evaluate the shift duration as it compares between the planned shift duration and the actual shift duration. The third addresses the productivity and compares between the actual throughput and the bottleneck rate. In this case, the spreading rate. The waste was evaluated according to the waiting times and the overprocessing. The WIP and the cycle time enable us to evaluate the flow as they were compared to the critical WIP and to the raw working times. Accordingly, we were able to present a color-coded pie chart that represent the status of production according to the planning reliability, the productivity, the waste, and the flow. And this type of representation we were able to present per location and per shift, and this might enable decision makers to evaluate their production strategy and their results. I will conclude this presentation by stating that the combination of advanced technologies available today with lean construction and production theory may significantly impact the processes, operations, and technologies in earthworks and road construction. Further implementation requires development and adaptation of production theory, so it would suit the unique characteristics of production that we can find in earthworks and road construction. Thank you.